So far we've talked about addition and subtraction in vectors. We're going to be moving on today to some new applications, and the dot product is the first one that we're going to be talking about. When we add or subtract vectors, a vector quantity is obtained, but this weird thing happens when we multiply vectors. We get a scalar result, so we're just going to get a number. That scalar result describes how the vectors are positioned with each other. And I'm sorry in advance for some of the starting and stopping in this video. I'm attempting to make it with some crazy toddlers running around. The first application that we're going to be talking about might be familiar to you if you took physics. So we're going to be talking about work. Work is a scalar quantity. And the formula for work is force dot S. So this force is the force that's used in displacing an object, so moving an object through vector S. I'm not going to go through an example quite yet because I do need to kind of back up and explain how you do the dot product, but we will get to one later today. So the definition of the dot product: suppose two vectors, vector A and vector B, are non-zero vectors arranged tail to tail, forming an angle theta. Theta is going to be between 0 and 180. The dot product A dot B is defined as the magnitude of vector A times the magnitude of vector B times cos of theta. So I'm just going to draw a quick little picture right here. If I have vector A arranged tail to tail with vector B, theta is going to be the angle in between those. And I know I said it before, but I'm going to say it again. I just want you to remember that the dot product of two vectors is a scalar, not a vector, so it's going to be represented by a real number. We're going to start off with a really easy question. So given the magnitude of vector A is 3.7 and the magnitude of vector B is 4.9, and the angle between the two vectors is shown. So if you look at the diagram, you can see that the angle between A and B when they're arranged tail to tail is 25 degrees. Find A dot B. The first thing that we're going to do is write our definition. So vector A dot vector B is equal to the magnitude of vector A times the magnitude of vector B times cos of theta. So I can go ahead and just start plugging in my values here. So A dot B is equal to 3.7 times the magnitude of B, which is 4.9, times cos of my theta, which was 25. And if I multiply all of those together, I'm going to get a value of 16.4. I'm going to extend this question just a little bit further. So the first part is, what happens when the vectors are perpendicular? So if I have two perpendicular vectors, it means that they meet at a 90-degree angle. Now, for all of these questions, the determining factor is going to be this cos of theta. The magnitudes of the vectors won't really change anything here. So if I think about what happens if I have cos of 90, I would hope that by now you all know that that's 0, which means that no matter what I have for my magnitudes, I'm going to be multiplying by 0, so the dot product is going to be 0. Now I can think about the next two parts the exact same way. What happens when the angle is acute? So what happens if my angle is less than 90 degrees? Cos of anything less than 90 degrees, or even 0 to 90 degrees, is going to be in quadrant 1, which means that we're going to get a value that's going to be greater than 0 for A dot B. Now the exact same thing for the last part. What happens when the angle is obtuse? Well, that means that our angle is going to be between 90 and 180, so it's going to be in quadrant 2, and we know that cos of anything in quadrant 2 is going to be negative. So A dot B oops, there we go, is going to be less than 0. I had to make them a little bit smaller so I could fit in this last one, but what happens if the angle is 180 degrees? So we know that cos of 180 degrees is -1. So this one's a little bit different. A dot B is going to be the magnitude of A times the magnitude of B times -1. Now maybe you're wondering if you can use the dot product for Cartesian vectors, and the answer is yes. So if I define vector A as A1, A2, and vector B as B1, B2, then the dot product is going to be A1 times B1 plus A2 times B2. So you'll just multiply those two x components together and then add the multiplication of the two y components. So we're going to go through a couple of examples now. So example 2 says, calculate the dot product given each set of Cartesian vectors. So 3, 1, dot 6, -2. So the first thing that I'm going to do is multiply the x components. So 3 times 6 is 18, and then I'm going to add the multiplication of the two y components. 1 times -2 is -2. 18 plus -2 is 16. Part B says -1, 4, dot 6, -8. So again, I'm going to multiply those x values. -1 times 6 is -6, plus 4 times 8 is, 4 times -8 is -32, and then I'm going to get -38. So example 3 says, calculate the value of angle E to the nearest degree in triangle DEF given the vertices D, E, and F. So I quickly drew in a little sketch here. I know that I'm looking for this angle right here. I also know that in order to do this, I need to come up with some vectors. So I need to come up with vector ED. I'll just use red, I guess. And then I need to come up with vector EF as well. So remember, these need to be tail to tail, which is why E is first in both of these. So if I'm looking at vector ED, I need to use the points in D and subtract the points in E. So -2 subtract 1, -3, and then I'll look at my Y's. 6 subtract 2 is 4. And I'm going to do the same thing for EF. I'll take the points in F and I'll subtract the points in E. So looking at the X's, 5 take away 1, and then looking at the Y's, 4 take away 2. Now if I think about my dot product formula, the only thing that I can really do now is calculate the magnitudes of ED and EF. So I'll do the magnitude of vector ED first. So I'm going to get the square root of -3 squared, so 9 plus 4 squared is 16, which is the square root of 25, which is 5. There we go. And then the magnitude of EF, I'm going to take the square root of 4 squared, which is 16, plus 2 squared, which is 4. So the square root of 20, and I can break that down into root 4 root 5, which is 2 root 5. So on the last slide, we talked about finding the dot product for Cartesian vectors. And we went through a formula, A1 times B1 plus A2 times B2. We can calculate the dot product of ED dot EF right here. Now that won't necessarily give us angle E. When we're using the formula for dot product for Cartesian vectors, there is no cos of theta, so we're not using an angle in there. But just off to the side, we are going to calculate ED dot EF, and if you don't already know why, you will very soon. So if I do that, I'm going to get, and again, I'm just going to use some red up here, I'm going to multiply my x values, so -3 times 4, plus my y values, so 4 times 2, and that's going to give me a -4. So I've rewritten my original definition for the dot product, and now that I have all of this information that we just found above, I can go ahead and plug in what I know. So I found ed.ef. I know that this is -4. I also found the magnitude of ed, 5. I know the magnitude of EF, 2√5, and the only thing that I don't know is cos of theta. So hopefully by now it makes sense why we did all of this work. I'm now able to take this original definition and rearrange it so that I can find my missing angle. So -4 equals 10√5 cos of theta. I'm going to divide by 10√5. So I'm going to get -2 over 5√5 equals cos of theta. So in case that was difficult for you to see, I guess, I did -4 divided by 10√5 equals cos of theta, and then I just simplified that. And then if I want to do the cos inverse, I'm going to get my theta to be approximately 100 degrees. All right, and for our last example of the day, expand and simplify. So here I have 2u plus v dot u minus 2v. So when you're doing a question like this, you do need to think basically about FOIL. So I'm going to dot each of these terms with the other terms. So I'll do my first terms first. So I have 2u dot u plus my outside, so 2u dot -2v plus my inside v dot u, sorry, there we go, plus my last v dot -2v. Now, if I think about this first term, 2u dot u, I have a vector dot the exact same vector, so the angle between them is going to be 0. Now, we know that cos of 0 is 1. So basically, 2u dot u is just 2 times the magnitude of u times the magnitude of u times 1. So 2 times the magnitude of u squared is how we can simplify that first term. Now for the next term, I'm going to look at my coefficients. So 2 times -2, so I'll get a -4. And I'm just going to keep it as u dot v. Plus, I can't do anything with the next one either. So v dot u. And then minus 2. And here again, I have a v dot v. So angle is 0. Cos of 0 is 1. When I plug that into my formula, I'm going to get the magnitude of v squared. Now if I look in the middle, I do have some like terms. So since the vectors are arranged tail to tail, u dot v is the exact same as v dot u. So I can simplify this a little bit. 2 times the magnitude of u squared minus 3 u dot v. Now if you wrote v dot u, that would be okay too. I'm just going alphabetically, and then 2 times the magnitude of v squared. One final thing that I want to just remind you of, you must always use a dot if you're trying to represent the dot product. So you're not allowed to use a multiplication sign. This will actually have more meaning in the next couple of lessons, and you can't just write them in brackets like this. This actually has no meaning whatsoever.